All right, well, now we're ready to go. So I'm going to talk about a little bit of my research that I've been doing for graduate school master's thesis, and it's looking at avalanches that fail on deep, persistent weak layers. And I have a data set from Bridger Bowl. You could also call them deep slab avalanches, but I've put a little bit more specific definition in there. A lot of work's been done on deep slab avalanches, and the way they're defined varies from anything over 3 feet or a meter to something that's failed on a weak layer that's older than a certain time period, or crown depths that are greater than a certain percentile of regional crown depths. But I looked at avalanches that I thought failed on deep, persistent weak layers. Before I go much further, I'll just say a quick thanks to my committee, Jordy Hendricks, Carl Berkland, Kathy Irvine, the American Avalanche Association, and Friends of the Avalanche Center for some financial support, and Bridger Bowl Ski Patrol and Big Sky Ski Patrol for providing some data sets and a lot of conversation about this stuff. So I'll start with just an overview of deep slabs and challenges with those, and then a brief intro to the study area and the data sets I was using, and then my methods for finding deep slab avalanches and the statistical methods I used, and then my results and the summary. So I was interested in deep slab avalanches as Bruce showed earlier in that first graph with the crossing lines. They're hard to trigger. The likelihood becomes low, but the consequences become higher. The propagation propensity is higher. They'll fracture across starting zones and around ridge lines and create really large destructive slides. Compared to new snow instabilities, they're a lot harder to forecast. With new snow, we look for some bullseye data like recent loading, widespread recent activity, and that usually heightens our awareness of the hazard. And we see a lot of activity with that on freshly buried weak layers and fresh snow. With deep slabs, we see them after new loads and stuff, but not as frequently. We'll get a lot of load throughout the season, and then finally one happens. It's kind of hard to predict. We kind of wait for it. And they're accompanied by little evidence of other avalanches on that layer. And then furthermore, a lot of conventional stability tests are hard to interpret or don't work well, like the ECT is only really good to 70 centimeters or a meter. And then some tests do work, the deep tap test and the PST. Discussed a lot of those earlier, but as with any test, you kind of have to know them for yourself, get a lot of practice with them, and they're not really the key to, or the answer to your instability question, but they can be helpful in solving the problem. I'm mostly interested in what types of weather patterns we see associated with these early in the season when the weak layer is forming, and then on the days preceding these events. So I used a data set from Bridger Bowl. A lot of you are familiar with it. It's out there. Can't see it. We're like right there. It's a north-south oriented ridge line, mostly east aspect with some north and south aspects from sub-ridges. And the climate's an intermountain climate, so it's kind of between continental and maritime. Continental being dry, shallow snowpack, depth hoar all the time, like Colorado, and maritime being deep, wet snowpacks with not very many persistent weak layers. This season's a pretty good example of that, with some deep, persistent weak layers, but also a lot of snowfall. So pretty good intermountain season we're having here. So the data set I used to look for avalanches on deep, persistent weak layers was from 44 years of avalanche control data. So I searched through all the records from the 1968-69 season to 2012-13 last season. And this data set includes all explosive triggered avalanches, almost all skier triggered or natural avalanches over size greater than or equal to R size 2. And then a lot of, but not all, large out of bounds avalanches, natural and skier triggered. Pretty good amount of the avalanche terrain at Bridger's shown here. Steep, rocky, a lot of little isolated kind of starting zones, a variety of north to south aspects. So I use these records to find avalanches that failed on persistent weak layers using avalanche characteristics that are typically recorded with those like layers involved, crown depth, R size, avalanche type, and triggers. And so my definition for deep slab is, as I've said a few times, avalanches that fail on deep persistent weak layers. And then I focused on those that occur late in the season, so February, March, and April. That's when it starts to become a little more difficult to forecast. We feel like maybe it's getting stable, but the weak layer is still there, and we see large slides on that. So in a lot of these historical records, the weak layers aren't known or recorded, the actual weak layer type. So I'm going off of the other things. I start with looking at layers involved. If it's recorded as sliding on the ground, I assumed it slid on a persistent weak layer, probably depth hoar. But not all depth hoar avalanches are recorded as sliding on the ground. If it leaves behind a layer, a thick layer, people recorded it as sliding in old snow, and higher up facet layers that aren't actually depth hoar wouldn't be recorded as on the ground. So I looked at all avalanches that had old snow layers involved and pulled out those with R sizes greater than or equal to 2 and crown depths greater than or equal to 36 inches. And I use 36 inches or 3 feet and not a meter or something because of the way they're recorded. They kind of rounded to a foot or 2 feet or 3 feet. So it's an easy cutoff there to get a good amount. And then from that group, I looked at all of those records along with weather records and other avalanches during those times. And if they were significantly deeper, crown depths significantly deeper than previous storms, snow, or other avalanches in that cycle, I considered them as sliding on persistent weak layers. And then required that they were either a hard slab or a wet slab if they didn't have if they weren't recorded as sliding on the ground, because it's unlikely we'd have a soft slab on a deep persistent weak layer late in the season. And then again, only looked at those in February, March, and April. So out of 44 seasons, I had 24 with avalanches on deep persistent weak layers late in the season. 5 of these seasons had only wet slabs, 7 had only dry slabs, and then 12 had both wet and dry slabs. And there were 76 days in those 24 seasons, a total of 196 events. 50 of those days had dry slabs, 26 had wet slabs. And there were a few wet loose included in there because they were recorded as sliding on the ground, and I figured if it slides on the ground, even if it's wet loose in February or March, it's probably destructive. Could have been an error in the record or something, but it's possible, and figured that would be worth keeping. So some of the characteristics of those slides, the 196, the triggers were mostly artificial explosives, pretty good amount of naturals and artificial skier, but it's kind of similar to what some other studies have seen. Scotty looked at a lot of deep slabs at Big Sky in 2006, and Comey and McAllister and Jackson in 2008, and they show smaller charges, smaller triggers are a pretty common trigger for deep slabs, showing that you don't necessarily need the big AMFO or a 9-pound shot for that. And then the distribution of crown depths on all those, kind of an average of 3 feet, some 1 and 2 and 4, and then tails off towards the deeper ones. This spike at 0 is from avalanches that were recorded as sliding on the ground but didn't have a crown depth recorded with them. So they end up down there. So my research questions or what types of data, what's kind of the bullseye data we should look for when forecasting deep slabs? With new snow, with our general avalanche problem, we're looking at, is there a weak layer, is there recent loading, what's the avalanche advisory saying, do we have a cohesive slab? With wet slide danger, we came up with this last spring when I had a knee injury and was sitting around all day. Do we have recent wet slides? So if we have recent deep slides, we're probably going to heighten our awareness of that deep slide. And I think this should probably be more in the center because it's probably pretty warm if they're all in bikinis.
What's the one with turf?
Oh, whatever Turk says, he's pretty getting close to the bullseye data. He's pretty in tune with the mountains and the snow. Just right on the outer edge there. So what I'm really looking at is what types of meteorological metrics are associated with deep avalanches on deep persistent weak layers. My first question is, what metrics early in the season, when that snowpack's forming, when those weak layers are being formed, are possibly different between seasons with these avalanches or seasons without? And then the second question is what weather on days preceding this type of avalanches is more associated with days that have this type of avalanche or days without. So to look at that, I compared weather between seasons with deep slab avalanches and seasons without. So I had 24 with and 20 without, and then compared weather between days with deep slab avalanches and days without. And to get an equal number of days without deep slab avalanches, randomly selected days from seasons that had deep slab avalanches, so I selected a proportional number of days without avalanches on deep persistent weak layers as the number of days with avalanches in each season, and selected those from February, March, and April when avalanche control was performed before the date of the last avalanche on a deep persistent weak layer. So that gave me a comparison between days where triggers were applied to the snowpack and an active weak layer was potentially down there. So we're not, after the last avalanche, I'm assuming that there's maybe a return to stability. But before that last observed avalanche, curious about what's different on those days that triggers are applied and nothing happens, than days when they're applied and something does. So the metrics I looked at between days with and days without avalanches without deep slab avalanches were started with those that are regularly observed at this ski area: snow depth, 24-hour new snow, minimum and maximum temperature, 24-hour snow water, and rain. And then from those I derived a bunch of kind of lagged variables. So what's the precipitation totals over 2, 3, 5, and 7 days, total water, total snow, minimum maximum average temperature over 2, 3, 5, and 7 days, total degrees above zero, change in snow depth over 2, 3, 5, and 7 days, and then just the temperature difference between the day before and the day of an event. And then seasonal meteorological metrics that I looked at between seasons with and seasons without deep slabs were summaries of all these, summarized by within November, December, and January. So average and maximum height of snow in each of those months, total average maximum new snow and new snow water, average maximum minimum temperature gradients, and then the proportion of days in each month with a temperature gradient greater than 10 degrees Celsius per meter and a snow depth less than a meter. This is kind of a proxy of how many days were there in each month that had conditions conducive to forming facet layer. And then those were all aggregated in November and December, December, and January as well. So to compare those, to compare seasons with and seasons without deep slabs and days with and days without deep slabs, I used classification trees, which are used to split out these two groups based on the thresholds of the explanatory meteorological variables into groups of just one or the other, and they'll hopefully make a little more sense when I show some of the diagrams up there. They've been used in a lot of studies to look at all weather between days with and days without avalanches, snowpack properties between stable and unstable profiles, wet slabs and glide avalanches by quite a bit of people. They've had 70 to 86% of correct classification of events with those. Without a cross-validated tree, which cross-validated tree is kind of statistically checked to reduce the error. These, when they're not cross-validated, they tend to over-predict on new data sets, but the full trees are good for explaining the underlying structure of the data and give us an idea of what variables are associated with the data set. So The results of the classification tree for splitting up days with and days without deep slabs is shown here. And so we see that the first variable split is on minimum temperature, and less than negative 9.5 degrees Celsius goes to a group with more days without deep slab avalanches, and then warmer temperatures go to more days with deep slab avalanches. And the next split is on maximum average temperature, or average maximum temperature over 3 days preceding the event. And that's warmer than 7.15 degrees Celsius, and implies that there's water going into the snowpack without any freezing. So sustained warming. Go in this direction where it's a little cooler. This last split is on snow depth change over 7 days. So less than a about negative 10 centimeter change in snow depth. So that's actually more settlement than negative 10 centimeters. And then this would be less settlement because there's greater than or equal to negative 10 change. So more settlements leading to days with no deep slab avalanches. And a couple reasons that might be was sustained high pressure, 7 days of high pressure, no load, snowpack kind of gains stability, adjusts to whatever previous changes. Or if it's a wet slab case, maybe there's just enough settlement that water's been pushed through the pack and created some drainage channels that allows it to flow through instead of accumulating along weak layers. Looking at this same data split up by dry slab and wet slab, and then the N is non-event. Similar splits in a little bit different order. It starts with the average maximum temperature over 3 days and goes down to more days with wet slab activity, so that's consistent with water and sustained warming and no freezing of the snowpack. And then when we go down to the warmer days with less settlement, we do see dry slab. So it's probably an extended period of high pressure that leads to these days without deep slab avalanches, even though there's a persistent weak layer down there. So this has a 77% correct classification. So it's kind of in the range of previous studies. And then for seasons with and seasons without deep slab avalanches, our first split comes from the total snow water in November, December, and January. And it's pretty, goes along with what you kind of think. Less snow water, drier leads to more deep slab avalanches. So we have shallower snowpack, drier days, clear nights to develop that depth hoar. And then wetter seasons are leading to seasons without deep slab avalanches. This next split's, a dry December, less shallower snowpack, less load on it, leads to more seasons with deep slabs. And then a wetter December with a deeper, this is maximum height of snow in November, so deeper November snowpack with a wet December is showing more wet or more seasons with deep slab avalanches, which isn't quite as intuitive as you'd think. So this one has an 87% correct classification. It's not cross-validated. The cross-validated tree with this just has this one split and a 75% correct classification. So in summary, with the daily metrics I found to be associated with avalanches on old persistent weak layers were warmer temps, sustained above freezing temperatures, and then more settlement equaling less avalanches, so high pressure kind of being a stabilizing factor. Other studies have found some similarities. This is more of a warming trend rather than just warm temperatures, as well as precipitation over several days. This is similar. That's total hours above freezing. Again, warming here. One thing that I didn't see in my data set was the substantial loading before days with deep slabs, and I think that's kind of an artifact of choosing days without deep slabs when there's avalanche control only, because usually you're doing avalanche control with a load. So both days without and days with had loading, but that kind of highlights that the difficulty of forecasting these when we keep getting loading and expect them, and then finally happens, but you can't really predict it. You can just wait for it if you know the weak layer's there. This settlement is kind of contrasting what Peitsch found, but he was looking at wet slabs more, and he found more settlement as more avalanches, and that's more proxy for more water going into the snowpack and creating more wet slabs, whereas mine is more in the dry regime. Seasonal metrics that I found to be associated with seasons with deep slab avalanches were the dry early season and then the deeper November snowpack, which isn't super explainable to me. Maybe just the fact that there's snow there in November gives it something to rot out. And then further is that the small triggers are more common than large triggers in triggering these, and this was seen in some previous work as well. And I think that's a really big point in that if a huge trigger's not triggering it, it's more about timing and location. You're hitting the sweet spot after a new load that kind of increases the number of sweet spots maybe. There might be one out there during a dry spell after you get 20 or a couple inches of snow water. You're going to have more sweet spots, and smaller triggers will be more successful in getting those to go. And that's the conclusion.
I was interested in your methods that wind wasn't figured in there.
Lack of data.
Okay.
Yeah, it plays a pretty big role, especially around here.
As you plot these over 44 years, does the incident seem to have a cycle to it? Did they cluster at the start of that set or towards the end of that set?
I think there's more towards the beginning, kind of consistently to the 90s, and then there's kind of a gap, and then a little bit more in the 2000s. I think some of that being at Bridger, the controls changed a lot since over 44 years, where no one was skiing the ridge 44 years ago, and now it's tracked out on a daily basis. So skier compaction and the controls changed from using artillery to hand charges, and might be an artifact of that time. There's definitely a bit of a temporal pattern there.
You're talking about the settlement in terms of the change in that was the change in the 7-day snow depth, was that right?
Yeah.
So you're not just talking about settlement, but you're also talking about accumulation. So that's
right.
That's actually that split. That split's helping to tell you that you're getting maybe a fair amount of accumulation during that time period.
Yeah.
Yeah, nice study, Alex. Is your 36 inches a maximum crown or an average crown height? Or?
Average.
Just elaborate a little bit more on what Mike was saying. When we looked at some of that statistics that Big Scott and what Scotty did earlier too, excuse me, we found that wind was like the biggest factor that correlated the most with it. I think that's for a couple of reasons. One is just increased loading, putting a bigger load in the starting zone. And the other one is the effect of explosives. If you have a harder, slabbier surface, the explosives are more effective at transmitting shockwave down to the weak layer. So I just kind of curious about if you've been noticing that, or you just didn't have enough data for the wind to incorporate that, or what your feeling is.
Yeah, I don't really have any wind data with this. Just snow, and the only thing I could come up with is lagged snow is something that's kind of available for transport, but nothing with wind direction or speed. So.
And we found a lot of times we'll get snow, a lot of snow, and we won't have a deep slab cycle. But if our deep slab slab cycles almost always correlate with a wind event also, at least the majority of them.
It speaks a little to the difference between the terrain at Big Sky versus Bridger, where at Bridger, most of the loading is right along the ridge top and gets daily attention. So rarely are those fractures up there more than, say, 3 feet, 4 feet. We might get some that, but unless they step down, they probably don't make it into this data set. Some of this data was certainly with the bad enough week layer that we were getting the cold weather, the drier slabs that were February, and some of those were initiated from that ridgetop wind loading, but we don't get the massive wind loadings, you know, the big open snowfields you guys are dealing with, so it's probably less wind affected at Bridger than at Big Sky.
Where are we now?
We dropped the danger low.
I mean, I can see like we're kind of in that holding pattern a little bit where we're probably not going to see deep slabs right at the moment, but like
my thoughts at this point are going towards the wet, but
yeah, so you're thinking more deep slabs now are going to be more associated with wet, deep wet slabs.
Unless we get like a huge storm, but we've had some pretty, I think that biggest load with like maybe 2 or 3 weeks ago, and it's like 2.5 inches of water, and we opened at like 11 o'clock or whatever, and I think that was the only time I saw anything step down in the back country. I think Argentina or Pinnacles went on that facet layer. So I think a load bigger or similar to that would be required for dry.
So you
Or hitting the right
think you're
spot.
going to see? Is this going to be a year with deep slabs in Bridger Bowl? Has there been in the ski area?
Can I try that one?
Sorry, Alex.
I think it's very dependent on how the warm weather comes in. If we go right to 5 nights and not freezing right now, the other thing we have going on at Bridger that's different from a lot of years is our extremely steep cliff bands have 1 foot to 2 feet of snow stuck to them, which is gonna be very good heavyweight triggers in the wet slide cycle. So given what we have for a moderate, let's say, in the kind of storms he's talking about, we don't have the December rain crust that we're dealing with. It's quite as scary as some years, but there is enough going on at depth that with all that stuff on those steep cliffs in 5 days of no freeze at night, we could have a pretty big show.
Yeah, I think the weak layer's still there. It's deep.
It's deep.
Oh, I just had 2 years ago when we did have our wet slab cycle within the Bridger Bowl region. It did go on consistent big layer, but we did have 3 inches of sleet previous to that. No freeze for three nights. And I think that's what you're pointing to. Those are obvious red flags for us to look for this coming spring.
Yeah.